I just ran a 30 million parameter large language model on this. This is the new SpaceMiT K3 Pico-ITX. It's a RISC-V single board, and it's a huge upgrade from the K1, which I reviewed previously on this channel. The K3 just came out, and honestly, there's a lot of things to like about this one. So much so that I had a hard time deciding what to put in this video. So I think in this video, I will give you my first impressions, and then we'll compare it to the K1, and we will run some benchmarks and show you exactly how to pull off the 30 billion parameter trick. Let's go. The K3 is one of the first consumer boards to implement the RVA23 profile, the new RISC-V standard that makes vector processing and virtualization mandatory. That means it ships with the RVV 1.0 vector extension and vector crypto instruction built in, so it can run standard Linux distribution compiled for RVA23. The actual board is a Pico-ITX form factor, which is 100 by 86 millimeter, but as you can see, mine came in an aluminium case. Looks great. I'll have to open the case in another video and look inside. It weighs about 620 grams with the aluminium case. So what's in the box? Not much. A little USB to jumper adapter. That's basically it. SpaceMiT also threw in this USB-C dongle, HDMI adapter, and a power pass-through. But that's an HP branded accessory, so I don't think that's part of the standard retail package. They just included it so I could film with it. If we look at the ports, we have a 10 gigabit per second SFP plus optical port, dual M2 slots, one B key, one M key for NVMe, Wi-Fi 6, USB-C with 65 watt power delivery, and a 4K display port over the same cable. And around the back, an FPC connector that exposes Ethercat and a CAN FD for real-time motion control. Okay, that's it. Let's boot it up. On the first boot, the setup wizard pops up. And the first thing I point out is that English is right there as a language option. That sounds trivial, but if you worked with Chinese-made software before, you know it's actually not. Looking at you, Kai Hong, Bianbu just feels like a normal Linux install. So we walk through the wizard, location, username, hostname, and you're done. Worth noting is that there is no network step in the wizard, so you have to set up Wi-Fi or Ethernet after the first reboot. So now reboot, log in, and you land in LXQT. So let's start with pulling fastfetch here and confirm what we're actually running. So okay, so here in fastfetch we can see we're running Bianbu 4.0 RC4, kernel 6.18.3 generic. Host identifies as SpaceMiT K3 Pico-ITX. So the platform supports is upstreamed properly. My unit is a 16 gig memory variant. There is also a 32 gig version with about 117 gigs of UFS storage formatted to ext4. The desktop, as I said, is LXQT running on Wayland, and there is actually a GPU on board too, a PowerVR B-series BXM 464. Bianbu is SpaceMiT's own Linux distro. It's based on Ubuntu, kernel is bleeding edge, and it ships with the SpaceMiT specific drivers and tooling pre-installed. Quick note for comparison fairness, the K1 in this video is on Bianbu 3. There is no clean upgrade path yet, so the software stack isn't identical, but it's each board running its current official OS. We'll come back to Bianbu later. On the spec sheet, the K3 is a generation ahead of the K1 in pretty much every dimension. Clock speed is up 50%, RAM goes from LPDDR4X to LPDDR5 at 6400 megatransfers. Storage upgrades from eMMC to UFS 2.2. That's about 3.4 faster according to SpaceMiT. And networking, the K1 had gigabit 8, the K3 adds 10 gig SFP plus and Wi-Fi 6. But the marketing claim that gets your attention is this one. The K1 was stated as 2 tops of AI performance. The K3 claims a 30 times jump in 1 generation, and we're going to find out whether that holds up. Slightly bigger board, dramatically more capable on paper. Now let's run the numbers. So let's start with the CPU. I ran sbc-bench on both. Same OS family, same compiler family, performance governor. And here is the main headline, I think. The AIS 256 encryption That's the workhorse for HTTPS, VPN, encrypted backups. Basically every secure connection your computer makes runs 36 times faster on K3 than K1. Not 36%, 36 times. Same algorithm, same data. The K1 has no hardware crypto. The K3 has the full RVA23 vector crypto extension set. And it just rips through AIS at a rate that competes with mid-range ARM software on chips. But it's not just crypto. Memory bandwidth is up 2.4. Memory latency is cut in half. 7-zip multi-threaded compression jumped from 6,740 MIPS to 19,480, about 2.9 times faster. Now the clock only went up 1.5 times, from 1.6 to 2.4 gigahertz. So the K3's per clock throughput is about 1.9 times the K1's. So that's not just more megahertz, that's actually a microarchitecture redesign and improvements, optimizations. Honestly though, I don't think you really need a benchmark to feel any of this. I noticed the moment I started using the desktop, the window manager feels snappy, opening apps is kind of instant, scrolling is smooth. Coming from the K1, it is a noticeable jump. So I built llama.cpp from source on both boards. Same revision, same flags, Q4KM quantization, 8 threads. First test QN 2.5, 1.5 billion parameter model, about a gigabyte on disk. Watch this, same prompt, both boards, both running mainline llama CPP. K1, 6 tokens per second, K3, 14.5, about 2.4 times faster. On the bigger 7 billion model, the K3 drops to 1.4 tokens per second. Usable, but very painful. The K3 managed 3.6, which is okay for short questions, but it's slow for anything substantial. But I had a feeling something was off here. So I was watching SpaceMiT's own demo video for K3. They have one on YouTube called K3 AI Large Model Demo on their channel, and I noticed something weird. The terminal in their video printed 2 lines that mine didn't. On the left, I have my mainline build, just standard llama CPP output. On the right, SpaceMiT's demo. It says CPU RISC-V 64 SpaceMiT. It mentions IME2, the integer matrix extension being active, and the CPU mask is hex FF0, which in binary is cores 8 through 15. None of that prints in my build. Whatever they're running, it's not mainline llama CPP. Worth noticing here, they're running a 30 billion model with 31.4 gigabytes of memory in use. Means they are testing on the 32 gig variant. We'll come back to that later. And look at this. Later in the same demo, they switched to an 80 billion parameter model. Different config, the CPU flips to FF, core 0 through 7. They switched to IME1 instead of IME2. Different cluster, different matrix units. So the K3 has 2 matrix extensions. IME1 lives in the X100 cluster up top. IME2 lives in the AI cluster below. SpaceMiT's runtime picks which one use depending on the model. That's quite sophisticated actually. So where did they get this magic build? It turns out SpaceMiT ships an optimized fork of llama CPP directly in the Bianbu apt repo. It's called llama CPP tools SpaceMiT. Sitting there, available on every K3 since the day this thing booted. One command later, I had a completely different llama CPP installed. Okay, so let's look at this mainline versus the SpaceMiT-optimized llama CPP and see what the difference is. So watch the HTOP windows here. On the left we have mainline, and on the right we have SpaceMiT. The mainline is running on processors 0 to 7, whereas the SpaceMiT build is running processors 8 to 15. So, and you also notice the speed, big difference. And here we go, same K3, same models, same prompts, just different binaries. On QN 1.5 billion, generation goes from 14 to 21 tokens per second, about 1.45 times faster. On QN 4 billion, 5.9 to 8.5, saved 1.43 times. On QN 7 billions, 3.6 to 5.2, again 1.45 times. The pattern is consistent across model sizes. That's what an architecture feature does. It's not a one-off, it's not a fluke. But I think the real story here is the prompt processing. That's the matrix multiplication heavy phase, where the input gets digested before generation starts. That goes up 4.5 times faster, 172 tokens per second on a Q1 1.5 billion. That's not just good for an SBC, that's actually really, really fast. And it does get better. So SpaceMiT is claiming that this board can run a 30 billion parameter language model. So I tried. The model is QN330B A3B instruct. It's a mixture of expert MOE architecture. So it has 30 billion parameters, but only 3 billion active per token. It's about 10 gigabytes on disk. Loading this model takes about 80 seconds because they optimized the stack before we load it. But this is a one-time cost and it's worth it. While that loads, let me talk about what I think about this thing. First, the obvious caveat, my unit has 16 gigabytes of RAM. So if you want to run a model that is larger than, say, 14 gigabytes, you will need more RAM. That's easy as that. To run a 30 billion parameter model, you need one that has been quantized a lot so that it's small. Yeah, I guess that's the trick if you want to run it on 16 gigs. So honestly, I'm very impressed. I wasn't expecting this type of performance at all. I thought it might have been, exaggerated in the marketing, but it's not. It's actually quite amazing. And there's so much more to talk about with this little guy. OpenHarmony is coming mid-May, 6.1, which of course I'm super interested in. That's my thing. And I want to test Bianbu more. I want to set up this machine as an open claw machine. And I also want to try setting this up as a build server for my other projects. There will be more videos on this soon. Also, there's some information that I'm lacking at the moment that I need to check with SpaceMiT themselves. For example, the price, which is obviously a huge thing. But this is really exciting time for RISC-V. This is a huge step in the right direction, I think. Anyways, thanks for watching. See you next one. And enjoy the output of the 30 billion parameter model. Ciao.